Yeah, I'm going to need some green chalk. Okay. Coming over here, we can parameterize our unit tangent vector in terms of S, which is distance traveled along the curve. So if our unit tangent vector is parameterized in this way, then it's kind of like moving along the curve at a constant speed of 1 unit per second. See how that works? Well, okay. Our unit tangent vector is a vector of magnitude 1. If we move from one position to another along the curve, then the only thing about our unit tangent vector that changes is its direction. So we sort of have a picture like this, indicating the first unit tangent vector and the second unit tangent vector, and the change in our unit tangent vector. Well, the change in our unit tangent vector is equal to the rate of change of our unit tangent vector with respect to position times our change in position. That's kind of a no-brainer. So here's our delta t, okay, the change in our unit tangent vector. That's this side of this isosceles triangle. Isosceles because both of your unit tangent vectors have magnitude 1. Now on the figure, our delta s, which is what we multiply by our derivative with respect to x of our s of our unit tangent vector, is the displacement from this point to this point. Now again, these two vectors are associated with this displacement. This is an isosceles triangle, and because our tangent vectors are tangent to the circle, and these are radial lines, the angle between our two tangent vectors, unit tangent vectors, is equal to the angle between our two radial lines. That means that this triangle is geometrically similar to this triangle, so that the magnitude of our change in the unit tangent vector over 1, which is a ratio of this side to this side, is approximately equal to our magnitude of delta s over radius of curvature. Now this is the magnitude of our delta s vector. And that's only approximately equal for small angles to the change, the arc distance that we've traveled. But clearly, if this figure represents two very nearby times, then this is going to be a very thin triangle, and this is going to be a very thin triangle. And the change, our displacement, delta s, will be very close to our arc distance, which is delta s without the displacement. And the notation might be a little confusing there. You see we have our radius of curvature here, so that our delta t, which is dt ds times delta s over 1, which is just going to be this, is going to be equal to our delta s over radius of curvature. And we see that our reciprocal radius of curvature is then going to be what we get when we divide the delta s into both sides here, the magnitude of delta s. And that's going to be our dt ds, the magnitude of dt ds. That needs an arrow over it. So that our curvature is the derivative with respect to arc distance traveled of our unit tangent vector. Now I'll try to make a little more sense out of why that is. That's not exactly a formal argument. It's not exactly a hand-waving argument. It comes down to the similarity of this triangle and this triangle, and this follows pretty much immediately. Let me try to make a little more intuitive sense out of that in another video clip.